Hey, hi everybody. I'm coming to you from the past. It's still Saturday night here on the East Coast of the United States. Um, and of course, we're in the Northern Hemisphere, so it's autumn here. Um, and I just wanted to come and talk about something that I'm really passionate about, which is file systems. And I realize that I'm maybe in the minority in that, but I really get into file systems, and I'm also particularly into Linux, having spent most of my career working in the Linux and Unix environment. So specifically, since we don't have much time, I wanted to drill in on XFS and recovering deleted data from XFS. So let me set the stage a little bit before we get into it. And by the way, if you have questions, I'm monitoring the general chat on my phone here off screen. So if you do have any questions, just throw them into the general chat, and I'll try and answer them in line. So XFS comes from SGI, long time ago, back in the 1990s. It was their attempt to create a high performant file system. These days, it's actually quite common in Linux operating systems. Red Hat adopted XFS as a default file system back in Red Hat, I want to say Enterprise 7. You also find it, I find it most often in my forensic work when I crack open one of these consumer grade network attached storage devices like a QNAP box or Synology NAS or something like that, because they're very often just embedded Linux systems running XFS over Linux software RAID. The problem with XFS and ZFS and a lot of these newer file systems is that we don't have really good forensic tool support. Xways admits to knowing something about decoding XFS, and there's a sleuthkit branch which has done some work towards including XFS support, but both of them, at least in my anecdotal work, have had some issues. So one of the things I'm going to demo to you today is using some lower level file system debugging tools, essentially in place of common forensic tools in order to get to where we need to get. XFS is, a modern 64-bit file system, blah, 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 all the sort of normal features that you would expect. One of the curious features about XFS compared to some other file systems you might have dealt with is that XFS is consistently big endian, regardless of the processor architecture that it's running on. So like if you look at an NTFS file system running on Intel, it's actually going to be little endian, just like the processor. The fact that everything in XFS is big endian turns out to be really helpful when you're looking at the file system, kind of through a microscope, like we're going to be doing here, because I don't have to worry about byte swapping and all that stuff. And I'll point that out when we get there. Uses extents to locate file content on disk. I'll explain something about extents when we get there as well. But basically, it's a typical kind of modern file system. And what we're going to do is we're going to basically reverse engineer the file system in order to recover deleted data. So what happens when you delete a file? When you delete a file in a modern file system, the file data doesn't go away, right? The blocks on disk that made up the content of the file are simply marked as unallocated. And they're available for some other file to come along and overwrite those blocks. But until that actually happens, the content of the old file that was just deleted remains on disk and can be recovered if you know where those blocks were. Now, in a file system, the thing that points to those data blocks and tells you where the file content is on disk is this metadata structure, which we call an inode, index node for short. So basically, every file has an inode associated with it. And the inode stores all the data about the file that isn't the file content. So it's like the timestamps on the file and the security settings on the file and things like that. So when a file gets deleted, the content of the file, the data blocks, get marked as unallocated. The inode also gets marked as unallocated, but also elements of that inode get zeroed out. The file size is in the inode is set to 0. Timestamps are updated, indicating the deletion of the file. But in XFS, unlike say Linux ext, the actual extent structures that say where the file content are not overwritten. So if you can find the inode that used to be associated with the deleted file, there's still kind of the mapping of where the blocks were on disk. So inodes are how the operating system keeps track of your files, but how human beings keep track of files is with a hierarchical file system. There are directories, which include subdirectories and files and things like that. So a directory in a file system is nothing more than a special kind of file that simply maps your file name, which is how you, the human being, understand files, to the inode number, which is how the operating system tracks your file. So when you delete a file, the directory entry for that file, at least in Unix file systems, is generally just marked as unallocated space, kind of slack space in the directory. Unix directories are very lazy. You just say, okay, this file has been deleted. But again, like the data blocks, the directory entry isn't overwritten. And so the old deleted directory entry is still visible. You can see the old file name. You can see the inode number that was associated with it and so on. And so combining all of that, it seems like we should be able to go through a directory file, look for the deleted entries that are kind of hanging around in the slack space, and then find the inode number associated with the deleted file. And using that, map to where the contents of the old file used to be on disk. And if those file contents haven't been overwritten, you should be able to get back the original file. Okay, so that's the high-level plan, right? And I'm going to kind of walk through that, in a little live demo for you. Okay, so let's talk about what a directory entry looks like. So a Unix directory file is basically just a sequential list of directory records, and the directory records are variable length. So each directory record starts with an 8-byte inode address. And then there's 1 byte that follows that, which is the length of the file name. And then the actual characters in the file name, however long that is, followed by a 1-byte file type, which says, is it a regular file? Is it a directory? Is it a link? Whatever. And then some padding, because these directory records need to be 8-byte aligned within the directory structure. And then a 2-byte offset, which is used for traversing the directory. It's not really important right now. Okay. So when a directory entry gets deleted, what happens is the inode address gets partially overwritten. Okay. So the first 2 bytes of the deleted entry get overwritten with all ones. So FFFFF. That indicates that this is a slack region within the directory file. It's unallocated space. And then after those 2 bytes of ones, there's a 2-byte value, which is the length of the sort of slack space that's available, because you may have deleted more than one directory entry. You may have deleted a whole bunch of files, which creates a large blob of free space. So 4 bytes, the upper 4 bytes of the inode address of the first deleted directory entry get overwritten. Now, XFS uses 64-bit addressing, but the reality is that addresses in XFS are actually variable length, and they often don't fill up the full 64-byte address space. In fact, it takes a fairly large file system, uh, over 512 gigabytes, to actually use more than 32 bits of inode address. And so for most file systems that you're going to encounter, or a lot of file systems you're going to encounter, the fact that the first 4 bytes of the inode address get overwritten doesn't really matter because they're all zeros anyway. And you can still see the remaining inode residue in the lower 32 bits and use that to proceed with recovering your file. So let me do an example for you. I'm actually going to do this live, and damn the demo gods, we'll see if we can get this done. So let me get over to my terminal window, which is where I live, and so what I've done here, I created a little test image to show you. So basically, what I did was I created an XFS file system. I made a file in temp. I deleted the file, and then I imaged the file system so that we could do this demo. So I've mounted that image on a directory called mount test, and so here's the mount command that I used, and I'm looking at the temp directory with the -i option, which shows me the inode number for the temp directory where I deleted the file. And that's where we're going to start with this little recovery exercise. So the command I wanted to introduce to you is a little command called XFS-DB. Okay, hold on a minute. Let me clean up my screen a little bit. Okay, so XFS-DB, and we're going to open the my CentOS file system image read-only, because we're going to be careful from a forensic perspective here. And XFS-DB is actually a debugging tool that was created by the XFS file system developers to help them debug, XFS issues. But we can actually use it as a forensic tool, and I've had to on many occasions when I haven't had a better XFS forensic tool available. So we're going to start by looking at inode number, this number, which is the inode for temp. Okay. And so one of the things you can do with XFS-DB is just print information in a file system data structure like that. So if I print the inode that I've selected, what you get is a breakdown of the information in the inode. You can see things like the timestamps, file size, and so on. And what we can see down here, this line right here, this is the extent list where the file, in this case the directory, content lives on disk. And there's only one extent, which starts at this block number and goes for one block. So it's a simple directory file. It only occupies one block. And we can look at the contents of that directory by examining that block. So I'm going to choose file system block, that block number. And I'm going to set my output type to text, which is kind of like the standard hex dump view that you all are probably used to. And when we print out that block, you get a nice little hex dump of the content of that block. All right. So over here, you can see the file offsets, and then the hex values, and then the actual ASCII interpretation. And right here, you see this file name called I'm deleted, which is the file that I created and then deleted just to make it easier for you to spot that. Okay. So these ASCII characters right here correspond to that, file name. But if you look back here, here's actually the beginning of the deleted directory entry. Remember what I said about the first 2 bytes being written as FF. And you can use this marker to find other areas in the file where, deleted directory entries exist. But this is the one that I'm going to pay attention to. So here's the beginning of a deleted directory region. Here is the length of that region. And then sitting down here in the last 4 bytes is what's left of the inode number that was associated with this deleted file. Right? And it turns out, because this is a small file system, you can actually see that only the lower 3 bytes of the address space are being used here. Right? So we can say, oh, look, okay, there's our inode number. Let me examine this inode using the XFS DB utility that we're sitting in right now. So I'm going to grab this inode number here. And I'm going to say, okay, I want to look at inode, this thing. I got to take the spaces out. Okay. And we can print that inode, just like we did with the inode for the temp directory. Now, so here, remember what I said. When a file gets deleted, like our I'm deleted file here, things like the file size get zeroed out, right? For example, the ctime value here actually gets set to when the file was deleted and things like that. And so because the file size is 0, what we don't see is the extent data that tells us where the content of that file used to be. Now, I told you that the extent data doesn't get zeroed out, but how do we see that? And the answer is we look at the inode in a hex editor, which, I realize for most people kind of gives them the heebie-jeebies, but for me, this is where I live, right? And so let's take a look at the inode, not in this nice interpreted format that XFSDB gives us, but in the raw hexadecimal, because it's good for you and it builds character. Okay, so here is the hexadecimal view of the data in the inode. And you can see this is actually, the inodes in XFS are 512-byte data structures, and they pack a lot of information into those 512 bytes. The first part of the inode here, the first 176 bytes, which I'm highlighting, is what's referred to as the inode core. And that's where stuff like timestamps and stuff are kept. Immediately following the inode core, though, are the extent structures. And the extent structures are these 16-byte records which tell you where the blocks are on disk. And it looks like there are actually multiple extent structures here. It turns out, in this case, though, that the file that I created was actually only less than a block long, and only the first of these extent structures matter. What you're seeing here, though, is that these inode data structures are constantly being reused, and so these other extent structures are actually residue from an earlier file that was bigger, that occupied multiple extents. But it turns out, let's just unpack this first extent, okay? Now, all right, here's the lunacy that is XFS. And really, I want to find the person who designed the XFS extent structure and you just give them a big hug, because, wow. It turns out that extents in XFS are not byte aligned. What? Yeah, so here's the sad story, right? So you've got 16 bytes, right? And they decided that for whatever reason, it would be a good idea to align the fields in the extent structure not on byte boundaries. Okay, sure. So going through this, so the low 21 bits are the number of blocks in this extent, that is the length of the run of blocks that make up the extent, there's 52 bits for the starting block where the extent begins on the disk, 54 bits for the logical offset. So what that means is if you have a file that's been broken up into 5 pieces, you need to know the order to put those pieces back together in. So the logical offset is, this is piece 0, this is piece 1, this is piece 2, and so on. And then there's a 1-bit flag for pre-allocation, which is this clever thing that XFS can do to sort of save space ahead of time for a file that's about to be written. Okay, clearly this is wrong, right? I mean, there's absolutely no reason why this should be this way. I mean, the block count should be a 32-bit value. The FS block should be a 64-bit value. The logical offset could be, 31 bits and 1 pre-allocation flag in the upper bit that you could mask off. I cannot wrap my head around how we got here, but we just have to deal with it. It is what it is, okay? So what I've got to do is I've got to look at this crazy extent structure in my hex editor and somehow break it down into, the number of blocks and the starting block offset, which are the last 2 fields in this insane collection of bits, right? Okay, so here we go. What I'm going to do is, because I'm a Linux kind of command line nut, is I'm going to actually break this down using some command line tools. So you can see that most of the upper part of the extent is all zeros, right? So I'm just going to grab the non-zero portion of this and break it down into bits. Okay, hold on to your seats. Here we go. Let me pop this into a different window here. So what I'm going to do is I'm going to echo that sequence of hexadecimal. Okay. Need to, again, remove the spaces here. And I'm going to use XXD, which is a hex dumping tool, to convert the hex ASCII back into binary. So I'm going to use the hex dumper in reverse to convert that hex ASCII into binary. And then I'm going to use XXD again to dump it out in bits, not in bytes. And we'll do 6 columns of bits. All right. Okay, so here are the bits in this hex value. Now remember, the low 21 bits are the block count. Okay. All right, so hold on. Let's count. It's 8 bits, 16 bits, 1, 2, 3, 4, 5. Okay, so that's 21 bits up to here. So this is the block count. 1 block, right? Okay. The rest of this is the starting block number. Boy. Okay, here we go. So I'm going to convert that from binary back into decimal. Oops, grabbed the wrong thing. I'm going to convert that from binary back into decimal. Okay, there we go. Getting rid of the spaces again. All right. Okay, so that binary number in decimal, 1142794. Okay, so that is the starting block number. Let's go back into XFSDB with that number. I'm going to select FS block, that number, type text, print that sucker for me. You can see it's mostly nulls because it's a small file. But up at the top, here is the content. It's a flag with a hex value. You're a grand old flag. You're a high-flying flag. So, and then the rest is nulls because files in Unix file systems, the slack space is null filled as a general rule. Okay, so cool. We were actually able to find the content of that deleted file using this crazy XFS DB tool. Now, if you wanted to actually, dump the contents of that block in a little bit different format, we actually need to play around with the XFS addressing scheme a little bit. XFS addresses are actually packed structures, which include what's called an allocation group number and then a block within that allocation group. So we need to convert our FS block address into what's called the AG number and the AG block number. Oops. Sorry, it's just AG block. And we also need to know the size of each allocation group. Print AG blocks. Okay, so each allocation group is that many blocks big. With those numbers, we can do a little bit of fun with the DD command. So DD, from my CentOS image, my block size is 4K. My block I want is at the AG number, which is 1, times the size of the AG, which is this, plus the block offset within that AG, which is this. And I want that one block in the extent. And right here is the content of the file that was dumped out by DD. The rest of this stuff is just noise from the DD command. I'm too sexy for this file system, right? So the point is, this is obviously a tremendously manual process, and you wouldn't do this as a general rule, but it shows you, I think, how we as forensics people can kind of reverse engineer file systems and tease out the information that we're looking for, in this case, a deleted file. Obviously this would be automated by some sort of forensic tool, but I think it's interesting to at least see manually how the tool gets there. There's real stuff happening underneath it all. Okay, and so, whoops, no, I actually want to be back here. I'm at the end of my time, and appreciate you all listening. If you have any questions, my contact information is on the slide. This material that I'm presenting is actually a very small piece of a 4-day class in Linux forensics, which is available for free from the URL at the top of the slide. The QR code corresponds to that URL. It's a 4-day class on Linux forensics. If you download it with the BitTorrent link, you also get the lab virtual machine with actual hands-on labs that you can do along with the material. I'm happy to report I actually will be coming to Australia in April of 2023. I'll be teaching classes in Canberra and Melbourne. I will be teaching this material, 4-day Linux material. So if you actually would like to see me present it live, that's the other QR code. You can sign up for one of my classes. Whether you come to my class or not, I hope that we can get together and hang out while I'm in Canberra and Melbourne, and I plan to spend some time in Sydney as well. So hopefully we can get together. Drop me a line at my social media, and we will try and set something up.